Okay, so everyone, welcome to our student colloquium. I remind the students who take it as a course that your main job is to understand. And for that reason, you should interrupt the speaker without mercy, ask questions, and don't hesitate to raise your hand and unmute yourself and so on. And it's our great pleasure to have a speaker from Williams College, Steve Miller. I wish it was in person. I hope it will happen in person once the plague is over. But today it's on Zoom, and the topic is German tank problem. Steve, please, and I'll mute myself so my dog will not interrupt.
Okay, so thank you. It is a pleasure to be virtually here, and as was said, I hope to visit in the near future. I was supposed to be in your neck of the woods for an AMS sectional, but sadly that's, I think, being rescheduled. So what I want to do is talk about one of my favorite problems in all of mathematics, the German tank problem. And the reason I love it so much is you don't need to know that much to start working on it, but depending on which direction you go, it leads to a lot of wonderful mathematics, it leads to some open problems, and it leads to a great divide between doing theoretical math and doing applied math. And at times, there's a way to bring them together. And one of the greatest challenges is trying to come up with in math, well, what should I try to prove? And there's a way to go about this. One way is trying to find something that people will find interesting, and another is trying to find something where you have a chance of success. And so we're going to see some beautiful closed form answers for some of the problems, and we'll talk about the miracles that happen as to why we're able to get to these closed form solutions. All right. So as an introduction, this is a snapshot of what Europe looked like before the start of major hostilities in World War II and then in 1942. And you can click on the YouTube link at your leisure later and just see the expanding area controlled by the Axis powers. And so one of the reasons for their great success in the field was their masterful use of tank tactics. And so it became very important for the Allies to know how many tanks did the Germans have, how many did they have available, how many were deployed to various theaters. And so this is a picture of a tank factory. And then I'm going to try to do this through Zoom. So I hope people will speak up and answer. So if you are the Allies and you want to figure out how many tanks the Germans are producing, how would you do this? Anybody have any suggestions?
Spy on them.
Spy on them, excellent. So the most natural thing to do is to spy. And the question is, can you trust what the spies say? There is another way, and that's the way we're going to be talking about today, is mathematics and statistics. And given that this is a talk in a math department, almost surely the math stats will do better than the spies. So a little bit of background as to why I feel I am qualified to give this lecture. I spent 4 years at Yale College with a giant tank with a lipstick on top of it right outside my dorm window. So I have been looking at tank problems since my college days. All right. So here is the original formulation of the German tank problem. Imagine after a battle, you go through and you look at the damaged tanks and you see the serial numbers S1, S2, all the way up to SK. And it's important to remember that the Germans, when they were building their tanks, they had the serial numbers of the tanks in consecutive order. And there's a lot of reasons why you would do this. Well, it's the most natural as you're doing your counting. And second, if you look at the tank serial number, you can quickly tell when it was made. That can help you in terms of figuring out, is it time maybe for some maintenance on the tank? So there are advantages to something like that. Nowadays, a lot of times people try to hide information like that. If you are negotiating with a company and trying to decide, do you want to use them as a supplier? If they tell you, well, you're second order ever, that doesn't necessarily instill you with confidence. And so frequently invoice numbers and things like this are now a little bit randomized, so you don't know necessarily how many people have been using it. So our question is, assume the tanks were numbered 1 through n, we observe these values, can we guess how many were probably produced? And so this is the original formulation. So we will assume that the first tank is numbered 1 and the last is numbered n. I haven't been able to find in the literature what happens if the first tank is not numbered 1. It turns out it's not too bad to generalize, and I did this with some of my undergrads a few years ago, and you can come up with similar formulas. So what we want to do is we want to try to come up with the best estimate we can using the serial number. And what we're going to do is we're going to focus on the largest observed serial number. So we're going to call that M for the maximum. And so we want our guess to be a function not only of m, but the number of tanks we observe. Now, there's a lot of dangers in overestimating or underestimating. Can anybody give me an example of why it might be bad to have a wrong estimate either direction of how many tanks there are? What could happen?
If you underestimate, you might not be able to eliminate enough of them. If you overestimate, you may waste munitions.
Yeah, exactly. And so if we underestimate, we could go into battle and we could lose. If we overestimate, we might put too many forces in that one battle, and we might lose the ability to deploy those forces elsewhere. There's a lot of great quips attributed to Lincoln. One of my favorites from the Civil War: if General McClellan isn't going to use his army, I'd like to borrow it for a time. McClellan always believed that he was facing more tanks than he actually was. Not more tanks, more soldiers than he actually was. And this was analysis, paralysis by analysis. He just did not believe he had enough troops available to go into battle. All right, so for the talk, what I want to do is I want to give a quick sense of what are the mathematical preliminaries, mostly just binomial coefficients. I'll talk about the original formulation of the problem where you start at 1 in great detail. And then I'll give a sketch of how you would do it in the general case. And then as time permits, I want to talk about some of the issues that happen when you try to apply this in the real world. And this will lead to some great questions in statistics, but you can also turn this around and make it a talk on conjecturing. How do you come up with what you try to prove? How do you come up with the formula? And so while I give a theoretical derivation, it turns out if you look at the data by just simulating the problem, you are actually led to the conjecture that turns out to be true. All right, so the preliminaries. So I'm going to assume everybody has seen the factorial. N factorial is the number of ways to order n objects when order matters. N choose k is the number of ways to choose k objects from n when order doesn't matter. And then we have the binomial theorem, x plus y to the n is the sum of n choose k, x to the k, y to the n minus k. We're going to use, surprisingly, Pascal's triangle numerous times. And there's a couple of relationships that we need. The first is the most common, that any element, say 10, is the sum of the element above and to the left and above and to the right. So n plus 1 choose k is n choose k plus n choose k minus 1. There's a lot of ways to prove this. One is we can just use the definition of n choose k and just write it as ratios of factorials, clear the denominators, do some algebra, and everything settles at the end. I prefer proof by story. And so given that I taught a while ago at Ohio State, and Ohio State and Penn State are, I think, on course to clash this Saturday, I thought rather than do that, I'll do Red Sox Yankees. So imagine there's n Red Sox fan and 1 Yankee fan, and you want to form a group of k people. How can you do this? And so a lot of combinatorics comes down to counting something 2 different ways. Well, I have n plus 1 total people. I want to choose k, so it's just n plus 1 choose k. But another way of looking at it is I could not choose the Red Sox. I could not choose the Yankee fan. There's 1 choose 0 way of doing that. And then I have to choose k Red Sox fans and choose k. Or a completely disjoint case, I choose the 1 Yankee fan, 1 choose 1, and then I have to choose k minus 1 Red Sox fans. And what's nice about this is it's the same as the formula above. We just have 2 factors of 1. And now you can see the upstairs always sums to n plus 1, and the downstairs always sums to k. All right. The next thing I need from Pascal's triangle is going to be another relationship. 1 plus 2 plus 3 plus 4 is 10. 1 plus 3 plus 6 plus 10 is 20. That basically, as you go on diagonal sums from the right to the left, it is related to another element. And if you think about this a little bit, we'll prove it by induction in a moment. This isn't entirely surprising because we're getting this number by summing other things. There are, of course, a wealth of other properties of Pascal's triangle that we could cover. They're not really relevant to the talk, so I'm not going to go into great detail, but it would be remiss not to just point out one of your favorite examples. If you put a dot for every odd number and remove it if it's an even number, you get beautiful fractal patterns. You get basically the Sierpinski triangle. And I actually wrote a Mathematica code. There's a link to do this on the next slide. It was just easier for me to have the triangle not going from the top to the bottom, but going from the left to the right. All right. So here is the second relationship I mentioned, and this is the relationship that's responsible for the miracle. This is why we're going to be able to get such a beautiful closed form answer at the end of the day for a prediction for how many tanks there are. And it's, as I said, it's this diagonal sum, m choose k from k to n is equal to n plus 1 choose k plus 1. So the proof is a very straightforward proof by induction. And so we fix k, and in the base case when n equals k, it's just immediate. And then the inductive step, it's the same as almost all inductions. If you want to prove the sum of integers to the first power, the second power, when you add one more, you just use the inductive assumption for the previous. And so we can replace our sum over here by n plus 1 choose k plus 1. And now we just use Pascal's identity to get n plus 2 choose k plus 1. And that completes the proof. And this is going to be the identity that will drive everything that happens in the future. Okay, so ready for the next question. How should n hat, our best guess on the number of tanks, depend on m, the maximum tank number observed, and k, the number of tanks observed? Does anybody want to give me any thoughts about the functional form? Can you give me any bounds on n in terms of m and k? Thoughts on a lower bound?
It should probably be between m and 2m.
Okay, why between m and 2m?
So the maximum, it has to be greater than or equal to that because you've already observed that number of tank. 2m because assuming you've observed at least one tank, that's, you can say it's kind of like your average, and so you could double, and if you observed a lot more than that, then it would be unlikely that all the tanks are in the bottom half.
Excellent. So it should be somewhere between m and 2m. It has to be at least m. And so I might want to write it as m plus something else. And if you want to try and think, well, what could this form be? The larger m is, maybe the more I should inflate my guess. So maybe g should be increasing with m, for fixed k. And if I fix m and I observe more and more tanks, the more tanks I observe, the less I should inflate by. So maybe this should decrease as I increase k. So the simplest possibility is that it should be of the form b times m over k. The actual answer is very close to that. And so for the actual answer, it's n hat, our best guess, is equal to m times 1 plus 1 over k minus 1. So basically b equals 1, and there's a little bit left over. So if you want to see if something is reasonable, it's always a good idea to look at extreme cases. And as was remarked a moment ago, if we only observe one tank, our best guess is it's in the middle. So we would expect it to be around n over 2, so we should double it. And when k equals 1, we see, yes, we are doubling. The other case is, imagine we observe every single tank. We may not know that we observed every single tank, but imagine we observe every single tank. So if k equals n, you can see that this formula is also going to work, that it's going to inflate it not at all. So how are we going to get to our best estimate? Well, we're going to let m be a random variable, which is going to be the maximum serial number observed. And we know that it can't be smaller than k because we observe at least k tanks. And we know it can't be larger than n because that's how many tanks there are. So the probability of observing little m for the largest serial number is 0 if k is less than m, less equal to m, less equal to n. And for the intervening ones, it's equal to either of these two expressions. And so there's a couple of ways we can see this. The first expression over here, we divide by n choose k. That's the number of ways we could choose k tanks from n. And we want to look and see how many of those choices have little m as their largest serial number. Well, there are n choose k choices that have the largest serial number at most m, because we can't choose anything larger than m. But not all of these will have m as their largest serial number. So we subtract all the ones that have m minus 1, that have nothing larger than m minus 1, but don't necessarily have m minus 1. And then we'll be left with the number of choices of k tanks that have m as their largest. You could use Pascal's identity now to give the expression on the far right, or another way of looking at it is to say, well, if I want my largest serial number to be m, then I have m minus 1 values left over, and I have to choose k minus 1 of them. And that's another way of getting the expression. So now that we have that, we can calculate the expected value. So the expected value for our random variable m is going to be m times the probability that it equals m. And so when we substitute, we get a nice formula involving a sum and a ratio of binomial coefficients. So now we just do a little bit of algebra. So we expand out the binomial coefficients. And then after a little bit, we say, well, we have an m minus 1 and an m. They clearly are screaming, combine me. We've got a k factorial, m minus k factorial. You can begin to see it's looking a lot like maybe there's an m choose k coming into play. So we put all those stuff together. We pull out all the stuff that doesn't depend on m because it's not going to be changing as we sum. And then this is where the miracle happens. There just happens to be a closed form expression for the sum of m choose k. And that was the second binomial identity we talked about that gives us our n plus 1 choose k plus 1. And then we just put in what is that equal to, and then things simplify remarkably. Well, this gives us the expected value of m as a function of n and k. We can now just write in the other way around. We can solve for n in terms of the expected value of m and k. And there's our formula completing the proof. So it's actually not that bad to show that this is true. For the new problem, we have to tweak it a little bit. So we want to know how should n hat, our best guess for the number of tanks, depend on, say, the minimum and the maximum observed values. And so the setup is very similar. We would expect it to be s, where s is the spread, it's the difference between them, plus some function that depends on s and k. And then similarly, it should grow with s and decrease with k. Any thoughts as to why we might have a k minus 1 and not a k in the denominator? Why this is a natural thing to conjecture? So if you've done any statistics, one of the things you learn in statistics is the definitions of things like the sample variance. And you don't always divide by the number of observations. You sometimes divide by one less. And the reason is you want to be very careful about making predictions when you shouldn't. If I only observe one value and I observe 90, what is your best guess for the mean?
The value you observed?
The value observed, 90. What's your best guess for the fluctuations about the mean if I only give you one value? Should you be able to make any guesses about fluctuations with one observation? No.
Not intelligently, unless you
Not
need
intelligently. Now that's a great way to phrase it. I do know a lot of people who sadly do make conjectures and policy statements without enough data points. But if we only have one observation, we should not be able to say anything meaningful about the variance. And this is why k minus 1 is the more natural thing. And when you do the algebra at the end of the day and the dust settles, you get 2 over k minus 1. And in hindsight, 2 is actually not so unreasonable. In the case when we knew the smallest value was 1, we had to go up. Now we have to go both up and down. And so it makes sense that maybe it has to be doubled because we're going in 2 different directions. You can also check it by looking at, well, what would happen if k equals 2? What would happen if k equals n? And you'll get similar results. The algebra is very similar. Now we want to calculate what's the probability that we have a spread of s. It's a little bit more involved than what we did before, but it's a very similar idea. The nice thing about Zoom is if you really care about the algebra, you can just pause the video and watch it, or just email me for the preprint. And then the rest of the proof is similar, but just a little bit more tedious algebra. There's a lot of multiplications by 1 or adding 0 to make it easy to use some binomial identities. If you really want to see the details, they're in the appendix at the end of the slides. So we now want to compare how well did the statisticians, mathematicians do versus how well did the spies do. And I went to Wikipedia, source of all knowledge, or at least sometimes source of all knowledge for something non-controversial like math, pretty safe. And you can see there is a real difference between what the statisticians are saying and what the spies are saying. It's also a little bit interesting as to these nice round numbers for the intelligence estimates. 1,000, 1,550. After the war, there was access to the German records, and you can see the incredible fit that the statistical estimates had versus the intelligence estimates. One of the points I like to emphasize, I do a lot of applied math, a lot of consulting. I serve on a regional school committee. It's not enough to get the math right. You have to be able to convince people to listen to your mathematical analysis. And from what people have told me when I've given this talk over the years is that they were able to convince the generals to follow what they were doing. One of my favorite stories along these lines for World War II is the Americans had cracked a lot of the Japanese code, and they knew that the Japanese were planning on attacking something called AF-15. And they believed that that was Midway. And they went to Admiral Nimitz and they said, we believe there's going to be a massive Japanese attack on Midway. And up until this point, the Americans had not been faring well in the Pacific theater. And Nimitz was afraid to go all in. If this is true, this is a tremendous opportunity. But if it's false and the Japanese attack elsewhere, if all of our forces are there, we are tremendously exposed. So he said, come back when you're sure. And what I love is the way they came back with certainty, the way they were able to convince him. And it shows that you don't always need the most advanced mathematics to have the greatest impact. What they did, either on a code that we knew was secure or in a special message sent in person, I forget how they did it, they sent a message to Midway and they told them to deliberately break one of their water pumps and then ask for a replacement and say that if you don't get a replacement in 2 weeks, Midway will be out of fresh water. A few days later, the Americans intercepted a Japanese transmission. And when they decoded it, it said, we have intercepted an American transmission from AF-15. AF-15 has a broken water pump and will be out of fresh water in 2 weeks. And at this point, they were then able to go to Nimitz and say, we are sure it's Midway. And the Americans went all in, and it was the turning point in the Pacific theater. Phenomenal application of mathematics, but also of the ability to communicate with people. And so what I want to do now is, I'm not sure what everybody has done for statistics, so I want to quickly go through a little bit of regression. And then if you've seen this before, we will get to some new applications in just a little bit. So the idea is to find the best fit line to some observed data. And I know most data does not follow a line. We'll talk soon about how you handle things that aren't linear. And there are three natural ways to talk about error. So imagine we believe there's a linear relationship y equals ax plus b, and we observe at xi, we observe values of yi. So three ways to measure the error is we could look at just the error between observed and predicted, the absolute value, or the square. Can anybody tell me an issue with using just observed minus predicted?
Every data point can be really off and you can still get total error 0.
Yeah, in fact, if I start off with 2 data points, the bottom left of my screen and the top right, I could say the line between the two of them is to actually go from the top left all the way to the bottom right, because the large error on the left cancels with the error on the right. So the first one is clearly off. The second and the third, they're actually both good methods. The third is frequently the one that's used because the absolute value function is not differentiable. And if you use squares, all of the tools of calculus are available. The disadvantage is the third one is much more sensitive to one bad data point. but you don't have to do any computer simulations. You can just immediately write down an answer. And so that is why we typically measure things with the third. So the way we would do this is Calc 3 multivariable. We have a function of two variables. So remember, the unknown a and b, those are our variables, not the x and the y. The x's and the y's are the observed data. So we set the partial derivatives equal to 0 to find a candidate for the maximum or minimum. This will be the minimum because if you let a or b go to infinity, you can make the error arbitrarily large. And so we just take the derivatives, set them equal to 0. And then once we have them equal to 0, we now have, oh, I can just pull out the a's, and this looks like a matrix equation. And so when you solve it, you get your best fit parameters. A hat, b hat is the inverse of the matrix times this vector, or just solving explicitly, you have a formula for a and b. It seems like the bottom of b has been cut off. It's the same as the bottom of a. The big fear, of course, is when you're doing this, what if the matrix is not invertible? It turns out as long as you are not a complete idiot, the matrix will always be invertible. And what do I mean by that? We're trying to figure out how y varies with x. As long as at least two of the x's are different, the denominator, the determinant, is going to be non-zero. If all the x's are the same, let's say all the x's equal x, I could pull out an x here. I would have a sum of 1 times x squared, pull out an x squared, sum of 1. So you can clearly see if all the x's are the same, the denominator vanishes. A little bit more work shows that it will not be 0 if they differ. And the reason is essentially this is looking at the variance of the x's. And the variance will be non-zero if they're not all the same. Given that you're trying to figure out how y depends on x, in practice, you're never going to choose all of the x's to be the same. So this is not going to be any issue in implementing this. Now, as I remarked, most relationships aren't linear, but a lot of them are linear after you apply logarithms. So if you have y equals bx to the a, if we take the log of both sides, you get the log of y is a log x plus little b, and that's going to be linear. And now we can use the method of least squares. One of my favorite applications of this is to Kepler's third law. So if t is the orbital period of a planet which is traveling in an elliptical orbit about the sun, we will assume no other objects exist in the universe, then the period squared is supposed to be proportional to the cube of the length. And of course, we could just take the square root of both sides so that the period is to the first power and get t is equal to some constant times L to the 1.5. So imagine we didn't know this. Could we discover this through statistics? Could we discover this through data? And this is what Kepler did. Kepler discovered this by looking at data from Tycho Brahe and others about the orbits of planets. Well, here is a list of the planets. I will sadly follow modern convention and remove Pluto. I'm measuring the distances in the planets in astronomical units. So the Earth is 1 astronomical unit away, and I will measure the orbital period in years. And again, you have a lot of freedom in terms of the choice of units to use. Anybody know, by looking at this data, anybody want to conjecture what B should be? So if you look at Earth, I've chosen my units very carefully so that Earth's period is about 1 and its distance is about 1. Therefore, with these units, B should be about 1. There's a lot of interesting units in the world. I will talk about one in a moment. But first, let's just see how good of a job the method of least squares does. When we actually use those values for the best fit values of A and B, we should be getting A is about 1.5, B is the log of 1, so it should be about 0. We see an incredible fit. So it does a phenomenal job. So I had mentioned interesting units. Does anybody know what unit is associated to this bridge? I grew up in Boston, so this is a very famous unit. It is the smoot. So smoot was an undergraduate at MIT, and he was pledging a fraternity, and the older brothers were curious, and they wanted to know how many smoots would it take to get from one end of the bridge to the next. And so that you can see they picked him up, marked him where he started and ended, and then they picked him up again, and they did this throughout the entire length of the bridge. And they found it took 364.1 smoots, and I love the plus or minus an ear, to get from one side to the next. Well, Cambridge wasn't thrilled with this, and they painted over the marks. The fraternity wasn't thrilled with this, so they did it again. And eventually Cambridge said, "Out of hell with it," and they left the smoot marks up. It's now been institutionalized, and there are now smoot markers on the bridge, and whenever there's an accident, they report on how many smoots from the end of the bridge did the accident happen. So this might seem like a silly story, but it turns out that this is related to one of the best lessons I give my students in life about being noticed. And we will return to this at the end of the talk. I'm going to just briefly mention the birthday problem because I know a lot of people have heard this over the years. Assume everybody is equally likely to be born on any day. How many people do you need to have in a room to have at least a 50% chance that two people share a birthday? And you can do this with 365 days in the year, or you could do it more generally with D days in a year. And it's a nice analysis using calculus and some approximations that it's about d to the 1/2 square root of log 4. And what's really important here is how it grows with the number of days in the year. It's like d to the 1/2. We could do some simulations and try to see the correct exponent. So we're going to look not for the 50% chance, but for the expected number of people in a room for the first collision, for the first time two people share a birthday. And when you look at this, this is beginning to look like real world data. It's spread out nicely, it's fluctuating. And when we try to do the best fits, I did 2 different sets of 10,000 simulations with D going between 10,000 and 100,000. And we see that A is really looking like about 1/2. And so it's nice support for the theory. I tried doing analysis of the German tank problem, and the first thing was just absolutely terrible. And what I looked at is I said, well, I know we have to have at least M tanks. Let me look at the best fit line for N minus M, the excess number of tanks, as a function of M over K. And so I tried to write it as some constant times M over K plus B, some kind of linear fit, and it's absolutely terrible. If I do a more general one, just plotting log of N against the log of M and 1 over K, you actually get a really nice hyperplane. And I don't want to go into too much detail about this, but just to show you that it does look like something is happening. What I want to focus on is the following implementation issue. Whenever you are doing mathematics, especially if you're doing something with applications, you want to ask yourself, is the answer reasonable? And so here, let's take the value K equals 1. So we only observe one tank. And I'm doing a huge number of simulations where the number of tanks ranges from about 1,000 to 10,000. And I'm plotting N versus the maximum observed tank. And I get, theory says N should be 2M minus 1. And in practice, I'm getting 0.784M plus 2,875. So when you look at this, what must be wrong about this? Why can't this be a good best fit line?
Well, just intuitively, it's nothing close to the theoretical estimate. So
it's not close to the
theoretical estimate. Maybe something's going on, right?
I'm sorry?
So that suggests maybe we're not quite there yet, right?
Right, but let's say we didn't know the theory was 2M minus 1. You should look at one of these numbers, either the 0.784 or the 2,875. One of them you should be able to say that can't be right. It can't work for all values of M.
For M equals 1, the 2,875 is really strange.
So one thing is if we have a small number of tanks, the 2875 is going to be a huge. But what happens as M gets very, very large? As N goes to, as if M is 1 million, we're only getting about 3/4 of a million. you shouldn't have your best guess n being smaller than your largest serial number. And as m gets very large, that's going to happen. We know it has to be at least m, so we know this can't be right. We can look at, see what would happen when k equals 2. Here, the best fit theory is 1.5. This is giving us 0.964. We go up to k equals 5. At least now, finally, we have a constant that's greater than 1, but it's still pretty far from the 1.2, which is best. We could look at the problem the other way, and we could say, well, what if instead we look at m as a function of the number of tanks? Because when we're doing the simulation, we're choosing some number of tanks, maybe 1,000, 2,000, 3,000. We choose, maybe take k equals 1 tank, k equals 2, k equals 5 samples from that, and then we see what the maximum observed is. So really, we should have m on the y-axis, not the x-axis. Even though when we go into things in practice, it's going to be little m that we observe, for the simulations, it's big N that we choose. And so if we do it this way, theory is m should be 0.5n plus 0.5, and we get 0.496n plus 10.5. So this is terrific. This is giving us a real sense of what's going on. If we try k equals 2, get another great fit, 0.667, 0.668. K equals 5, 0.883, 0.828. Still pretty good. One last thing I want to do before I end with the inference section is, here's another twist that we could do. I want to plot n as a function of m, the largest observed. But what we're going to do now is, for each value of n, we do it 100 times, and we record the value, the largest tank observed for each of those 100 trials, and then we average. So each dot here represents 100 trials. And what that does is it really cuts down on the variation. And now when we do that, the best fit line was supposed to be 1.5. Oops, this is a typo. This must be doing k equals 2, so it should be 1.5, not k equals 1, my apologies. And then the best fit is, again, very close to 1.5. All right, so the last thing I wanted to mention was, how can you use data to conjecture relationships in the world? So we know, from doing the theory, that n is 1 plus 1 over k times m minus 1. The minus 1 doesn't really matter that much. That's not a big deal. What we really want to understand is, how does it depend on m and k? And so let's say we do a bunch of experiments. And let's say we believe n equals am plus b. And we want to record what are the best fit values of a as a function of k, the number of tanks we observe. So again, the x-axis is the number of tanks observed. The y-axis is our best fit value of that slope a by looking at the data. And we believe, if we know theory, it should be 1 plus 1 over k, but imagine we don't know that it's 1 plus 1 over k. Can we look at this graph and see, yes, this is suggestive that a should be 1 plus 1 over k? Well, the first thing we could do is we could do a log-log plot. And when we do a log-log plot, I'm going to plot not a against, or log a against log of k, but a minus 1. And the reason is, we know that there has to be at least m tanks. And so when we try to figure out what the best fit slope is, what that best fit constant a is, we know it has to be at least 1. So let's subtract the information we know. So we're going to subtract off 1 from a, and we're going to plot the log of a minus 1 versus the log of k. Theory says that it should be equal to -1 times the log of k, and the best fit line we get above is equal to -0.999 log k minus 0.007. So essentially, 0 for that b, and we're really seeing that -1 for the slope. So what's wonderful here is that even if you didn't know initially that it was going to be a relationship like 1 plus 1 over k times m, we are led to that by looking at the data. All right, so the last thing I just want to end with is this idea of seizing opportunities. You never know where they will lead. And so I had mentioned Smoot before. He was the pledge who they picked up and they measured how far, how many of him he needed to cover the whole bridge. Has anybody heard of who Smoot is before? Anybody want to guess what he did with his life? You can't make this stuff up. He became the chairman of the American National Standards Institute and president of the International Organization for Standardization. And what I like to believe is that he took this, which might not have been the most pleasant experience as a undergrad, and he rolled with it. And this must have been a phenomenal, people heard about him through this. It must have been a wonderful way to introduce himself in various settings. And so always be thinking of what opportunities do you have around you? Who can you get to know? So here's a couple of references. I'm going to just quickly show the slides for how to do the calculation for the general case. Just so if anybody is truly interested, you can just hit pause on the video when it's uploaded and all the details are there. And thank you.
Thank you very much. Are there any questions? Steve, I have a question which is not directly related, but kind of philosophical. Why so many things in nature are described by power laws? You mentioned Kepler, but there are many other examples. Any comment on that?
No, I mean, that's a great question. One of the best explanations I know is from Feynman's lectures in physics, where he talks about why is gravity a 1/r² force. And what he says is if you're looking in a three-dimensional world, if you have some source of the force and you want to have a fixed amount of yankage, say, towards the center, then if the force is decreasing like 1/r², the surface area is increasing like r², and those two will perfectly balance. And so the total pull in will then be the same no matter what radius of sphere you have. And so in a three-dimensional world, you would expect gravity to be a 1/r² force. In terms of why so many things are power laws, great question. I don't know.
Thank you. More questions or comments? So I have another historical question. So you mentioned that statisticians did much better than spies, and this is a real life story, right?
Yes.
Are there any other examples when mathematicians beat spies? Anything related to warfare, common sense beating?
There was a story of classified, the yield of the Los Alamos bomb was classified, but they published the photograph of the explosion.
Yes.
And I forgot the name, but a British, I think, physicist was able to figure out using basically dimension analysis. He was able to figure out the yield.
Our laws in action.
Quantified, yeah.
And then it's not exactly related to your question, but one of my favorite examples of just applying mathematics in a good setting was the Berlin airlift. So in the Cold War, the Soviets closed off West Berlin to the Allies. But according to the treaties from World War II, the Allies had permission to fly planes over East Germany into West Berlin. They could not drive on the roads. The Soviets were able to close those off, but they could still fly missions. The problem was they had to now get all the supplies that West Berlin needed through the air very, very quickly. And this was one of the early successes of Operations. And what the general in charge did is he standardized everything. It was always the same planes were flying so that any pilot could fly any plane. They were loaded, they were launched at 10-minute intervals. And if it wasn't set up for you to land, you just went to the back of the line instead of just stalling and getting you in there that then had delays that would propagate through. And so there are lots of situations where very small math ideas ended up having tremendous impact. Southwest Airlines, I believe, operates on a very similar plan. I think all of their planes are the same. And this way, any pilot can fly any plane, any mechanic can work on any plane. You lose something with this. You might have a plane, and again, this is the pre-COVID era, where you don't have all the seats filled and a small plane would have sufficed, but you might have excess demand. But there's a lot of efficiencies that can be gained from something like this.
Well, that's why they're cheaper. Yeah, it's a budget.
Yes.
More questions or comments? Well, thank you very much. And you will put your talk on YouTube, right?
Yes. And so I will
email me when it's done, and I will forward this to our faculty and graduate students, those who missed your